Hi everyone, my name is Usman and welcome to my presentation on Smart Inspect, which is a microscale localization and classification of smartphone glass defects for industrial automation. Let's start. Here's the presentation plan, and I will firstly introduce the motivation behind this work, and in section 2 I will show you the challenges faced uh, while doing the manual smartphone glass inspection. And in the third part, I will introduce the Smart Inspect framework starting from the platform, and afterwards I will show you our framework results, both qualitative and quantitative. And at the end, I will show you some concluding remarks and future work related to this work. Okay, so let's start from the motivation behind this work. Um, Firstly, the production of smart device class has experienced a huge rise in the last 10 years. Technology companies who manufacture smart gadgets such as mobile phone, tablets, laptops, smartwatches, they produce millions of sets each year. The high volume of production means the inspection of the smart device class not only requires large manual force but also makes time another key constraint. And another factor is the average time for manually inspecting the glass of one smartphone is about 1 to 2 minutes. Um, uh, Therefore, meeting the immense market demand by increasing the production rate is becoming challenging without incorporating robotics, automation, and AI to the production lines to solve these inspection problems. And the human eye is only able to detect defects over 0.1 millimeter, which limits the accuracy of the inspection. Okay, so now the question is the problem with the glass screen. If we see the smartphone glass samples, let's enhance them for better visualization. Now you can see several defects and non-defect area over the samples shown in this slide. Um, for defect, you can see scratches and spears over the glasses. We used images having clear defect regions, uh, like big defects. Otherwise, it's difficult for better visualization in the presentation. So let's move towards the non-defect region on the glass, such as speaker regions. You can see uh, there are, this is the speaker region for this sample, and this is another. So there are some QR code you can find over the screens, and there are some camera regions which basically make light reflections by capturing the glass image, and here the button area, and there are also some other sensors regions which basically depends on different class types, like okay. So there are also some light reflections due to the edges, and you can also see the some fingerprints over the screens, and also the particles. And so all of these the regions, because of these these non-defect regions, like you, the system might take it as a defect. So uh, so let's move towards the contribution. Our contribution includes Smart Inspect can work on raw images, which I shown you in the earlier slide, and without any enhancement, and full smartphone glass images without any cropping. So this make it more powerful and efficient than the current state-of-the-art techniques. Usually people do the cropping of the transparent region, and then they do some apply some machine learning tool to detect the defects. And it also help uh, like in okay in precise localization and accurate classification of tiny defects, nearly equal to 5 micron that a human eye can't see. That shows the quality of our system. And uh, our system has excellent performance based on the partially labeled dataset, because we found that labeling a 16K image is really challenging. So that's why we introduce this work to label a large dataset. And so Smart Inspect enables a system for precise labeling of large dataset of smartphone glass with high accuracy. Okay. So here's the platform we made for the smartphone glass defect, and the size of the platform is 1500 by 500 by 400 mm, and we use line camera to capture a 16K pixel image, and the resolution of the whole image is around 16K by 24K, which is quite large, and the image size is around 400 megabytes. And so which basically enables us to detect the defects less than 5 microns. Okay, so let's go deep inside. Here you can see the inside view of the platform, and the top part has a camera, and this is the light, and the glass is placed on here on the conveyor, and the conveyor moves, and the line camera captures the image. So, and this is the side view of our inspection system. So how do basically mark the regions? So our system basically has 4 stages. In stage 1, all the suspicious white regions, white continuous regions on each image are cropped along their bounding boxes, which are detected by a counter finding algorithm. So here's the algorithm. It uses the non-maximum suppression after applying some cropping and some marking some regions, and afterwards like we will do resizing to each box to 2 to 4 by 2 to 4, and then we will in stage 2 a pre-trained convolution neural network ResNet is used to extract the feature of these crops for further transfer learning. And here's the stage 3 and 4 of our system. And in stage 3, based on the characteristics of our data set, we have only a few labeled defects and non-defect, light reflections due to dust and the sensor regions. So we use the BD classifier, which is a binary classifier that divides the top proposal region into 2 classes, defect and non-defect areas. It also controls the feedback iteration from unlabeled proposals to the k-means clusters. We use k-means several times and drop clusters excluding or containing a relatively low proportion of labels defects in each loop until the number of drop crops is less than the preset threshold. This stage cuts the redundant non-defect area crops and greatly reduce the actual number of defects. And at the end, in stage 4, a random forest is utilized. So we basically split it, the defect and non-defect. It's a 6-class defect classifier. So this is how we basically do semi-supervised learning for defect and non-defect regions. Okay, so now move towards the results. For qualitative results, we use a challenging and broken smartphone glass samples which has thousands of defects over it, and we applied the Smart Inspect. So let's see the results. Our challenge is firstly separate the defect from the non-defect regions. So let's see. You can see the purple regions are non-defect regions. So you can see the camera, speakers, some sensor regions. You can see it it successfully separated them and marked them as a non-defect regions. So we tested Smart Inspect on positive mark samples by human. We found that this glass has only one pit on it, and is marked with a green box, and this box is further enlarged to see the pit over it. And this is the second sample. And after applying, we found there are three regions. Two regions are speck of dust, which are marked by orange, and we basically enlarge these regions here and here. And one pit is found at the top edge of this glass, which basically missed by a human inspection. So we successfully found out and separate all the regions. Okay, so let's see the accuracy and quantitative results. We choose 4 different samples, and all samples have samples are inspected in a regular environment. We didn't use any dust-free environment. So you can see all the samples have light reflections, and they have sensor regions without any cropping, and all of them has a dirt. The speck of dust, like for the clean and scratch and pit crack sample, it has a very you can see the limited, but for the dirt sample we additionally put the dust over the sample. And for the clean sample, our system detected 133 regions, and so we found that it has around 97% accuracy to separate defect and non-defect regions, and also successfully mark if there is any defect. So in this for the scratch sample, so it's around 99, and for the pit and cracks, so our system detected 134 regions, and so we have a 94% accuracy. So if we like add the dirt, additional speck of dust over the samples, so sometimes the system basically take them as a non-defect non-defect region as a defect. Like sometimes the light reflection due to dust, that basically confuse system to make it a pit or something. So we observed that the system should be put in industry environment to avoid any false detection. So so you can see it significantly decreased the overall accuracy, but still it's 75% is still better, but we will recommend to use it for in a dust-free environment to avoid additional dust over a sample. So here's our conclusion. According to the experimental results, our semi-supervised method shows excellent performance with high accuracy at a microscale, and our system is capable of processing smartphone glass image as a whole without cropping the transparent region, and our approach has the ability to meet the high demand of quality inspection in production lines of several smart devices in order to compete the market. And in the last, current localization time of defects can be reduced by labeling and smartphone glass images using smart inspect. If you see, there are several methods which can give you some live detection, like live object detection, for example, faster RCNN, but that requires a huge label dataset. And as in our case, the main challenge is to label the image, and because the image size is really huge, and it's really difficult to label thousands of images of 16K images at a micro scale, and accurately like a label is also really challenging. So smart inspect can help in labeling images, large data sets, and that's further enables system to use by a faster RCNN or other uh, uh, object detection algorithm to reduce the inspection time. Currently, our inspection time is around 20 seconds, because image size is too large, and system needs uh, to to mark all the region and then apply the non-maximum suppressions to and close all the regions. Okay, so this is our work. Thank you for your time, and any questions?